Voyager wasn't meant to go this far, yet right now it's drifting through the place where the solar system actually ends and the galaxy begins. Decades after launch, its instruments started behaving strangely, sending back patterns no one expected, at the supposed edge of our sun's territory. In this video, you're going to ride with Voyager to that frontier and see what really happens when you finally reach the border of our cosmic bubble. You've been told the solar system ends around Pluto. Maybe someone mentioned the Kuiper belt, and that's it. That picture is not just slightly wrong, it's off by tens of billions of kilometers. You're not living near the edge. You're buried deep inside a much larger structure, and this real boundary is something you never see in the sky. So first big correction, the solar system does not end where the planets stop. Planets are just objects orbiting the sun. They do not define the system's border. What really matters is how far the sun's own outflow, the solar wind, can push against the material in our galaxy. The solar wind is a stream of charged particles, mostly electrons and protons, leaving the sun in all directions at hundreds of kilometers per second. As long as that stream dominates the local environment, you're still inside the sun's domain. In Voyager's direction, that influence reaches beyond 120 astronomical units, more than 18 billion kilometers from the sun, about 11 billion miles. Pluto orbits at roughly 30 to 50 astronomical units, so it's nowhere near the true edge. So if the edge isn't where the planets stop, what is it really? The answer is the Heliosphere, this huge, roughly bubble-shaped region where the solar wind carves out a cavity in the surrounding interstellar medium. The interstellar medium is the thin gas, dust, and magnetic field that fills the space between stars. The sun blasts into that material with its wind, pushes it back, and creates a zone where the sun's plasma and magnetic field dominate. Inside that zone, space weather is mostly solar. Outside that zone, it's mostly galactic. This structure is not just a geometric detail, it is a shield. Galactic cosmic rays, high-energy particles from events like supernova explosions, move through the galaxy at close to the speed of light. When they hit atmospheres, spacecraft, or people, they deliver a serious radiation dose. The heliosphere blocks a large fraction of the lower energy part of that flux, bends their paths, slows some of them down, and changes which energies actually reach Earth's orbit. You live under that protection every second, whether you think about it or not. So if we live inside this bubble, what are the actual borders? Where does one region end and another begin? Scientists break it down into three important layers. First, the termination shock. Close to the sun, the solar wind is blowing faster than the speed at which pressure waves can travel through that plasma, so it's supersonic in that medium. Farther out, it eventually hits the pressure of the surrounding interstellar gas and magnetic field. At that point, the wind suddenly slows from supersonic to subsonic, its density jumps, its temperature jumps, and a shock forms. That sudden change is the termination shock, the first big border. Beyond that is the Heliosheath. Here, the solar wind has been slowed and heated by the shock. It's thicker, hotter, and more chaotic than the inner wind. Flow speeds drop, the magnetic field gets disturbed and twisted, and the plasma is full of turbulence and small shocks. This region can be 20 to 40 astronomical units thick, so tens of billions of kilometers of messy, high-energy plasma between the termination shock and the final boundary. Then comes the heliopause, the real edge of the sun's bubble. This is where the outward pressure from the solar wind is balanced by the inward pressure of the interstellar medium. Inside the heliopause, most of the particles come from the sun. Just outside, most particles are interstellar. That's the boundary Voyager 1 crossed at about 121 to 123 astronomical units, roughly 18 to 19 billion kilometers, around 11 to 12 billion miles from the sun. In a physical, measurable sense, that surface is the edge of the heliosphere. Now here's a key question. If this boundary is so important, why do we only know it in detail along two thin paths in space? The answer is, only Voyager 1 and Voyager 2 have actually gone there. They launched in 1977 with a main mission that was supposed to last about 5 years, mainly to fly by Jupiter and Saturn, and in Voyager 2's case, Uranus and Neptune as well. No one expected, in practical terms, that they would still be returning data from more than 160 to 170 astronomical units away, over 24 to 25 billion kilometres, 15 to 16 billion miles, in the mid-2000s. At those distances, communication is extreme. A radio signal from Earth takes about 11 to 12 hours to reach them, and another 11 to 12 hours to get a reply back. So one question and one answer costs you almost a full day. The radio beam that leaves Earth and hits the spacecraft covers a gigantic area by the time it reaches their distance. From Voyager's point of view, Earth is smaller than a pixel inside that beam pattern, but with very sensitive antennas, the Deep Space Network can still pick out the tiny, low-power signal that comes back. So how did probes built with 1970s electronics end up doing cutting-edge physics in interstellar space? During the original grand tour of the outer planets, they carried instruments to study more than just planets and moons. They measured magnetic fields, plasma, and energetic particles all along their path. Once the planetary flybys were done, the spacecraft was still healthy, still spinning through space, so mission control just kept listening. The destination quietly shifted from outer planets to outer Heliosphere. That second phase is the one that matters for this story. After passing Neptune's orbit and leaving the known planets behind, Voyager 1 and Voyager 2 turned into pure boundary probes. They kept watching how the solar wind speed changed, how the density and temperature shifted, how the level of galactic cosmic rays rose as they moved outward. They were no longer mapping planets. They were mapping the Sun's territory itself, and then the transition into the galaxy beyond. This sets up the core question for the rest of the story, when a spacecraft actually hits that first border. The termination shock. What happens to the solar wind? What happens to the particles? And what do the readings look like when you slam into the Sun's outer wall for the first time in history? How do you know you've slammed into a wall in space when there's no sound, no light flash? Nothing obvious to your eyes at all. For Voyager 1, that moment came in December 2004, about 94 astronomical units from the Sun, roughly 14 billion kilometres out, around 9 billion miles. At that distance inside the heliosphere, the solar wind is still racing outward, but the instrument saw something change hard and fast. The flow that had been moving at more than about 400 kilometres per second, close to 900,000 miles per hour, suddenly dropped below the local sound speed in that plasma. In simple terms, it stopped being supersonic, it went subsonic, and that means, by definition, you've crossed a termination shock. Voyager 1 couldn't measure the bulk speed of the solar wind directly anymore. Its main plasma instrument had failed years earlier, so scientists had to piece it together from indirect clues. They watched how energetic particles behaved. They watched how the magnetic field changed direction and strength. They saw sudden jumps that matched what a shock should look like. You take the particle data, you take the magnetic data, you run them through models of how a supersonic flow slows down in a shock and the numbers line up. You're at the first big border of the Sun's bubble. For the first time, a human-made object had hit the place where the wind from our star physically crashes into the surrounding galaxy. If this bubble around the Sun were a clean, simple sphere, you'd expect every direction to hit that shock at roughly the same distance, right? Same star, same wind, same physics. But then you look at Voyager 2, and that neat picture breaks immediately. In August 2007, almost 3 years later, Voyager 2 crossed the termination shock at only about 83.6 astronomical units from the Sun, roughly 12.5 billion kilometres, about 7.8 billion miles. That's more than 10 astronomical units closer than Voyager 1's crossing, over 1.5 billion kilometres difference. That gap tells you something important. Fast. The termination shock is not a perfect shell centred on the Sun. The heliosphere is being pushed on and squeezed by the local interstellar medium and its magnetic field. In the direction Voyager 2 was travelling, the external pressure is higher, or the solar wind is reaching that region in a different way, so the shock is closer in. In Voyager 1's direction, the Sun can push a bit farther before losing, so the shock is farther out. Two crossings in different hemispheres already show that the sun's bubble is distorted, not a smooth sphere. Now, seeing that distortion is one thing, measuring exactly what the plasma is doing out there is another. And this is where Voyager 2 becomes crucial. You don't just want to know we hit a shock. You want to know how fast the solar wind was moving before and after, how dense it was, how hot it got, because those numbers tell you how strong the shock is and how the sun's outflow is interacting with the galaxy. Voyager 2's plasma instrument was still alive, so at around 83.6 astronomical units, it directly recorded the solar wind speed dropping sharply, from a few hundred kilometers per second to much lower values, subsonic in that medium. Along with that speed drop, the density and temperature of the plasma jumped. When a fast flow slams into a barrier and slows down quickly, a lot of its ordered motion is converted into random motion, which is what we call heat. So the particles crowd closer together, they move in more directions, and the temperature spikes. This is basic shock physics. The same principles used to understand shock waves from explosions or re-entry vehicles, just applied at a distance of more than 12 billion kilometers from home, in a plasma so thin you would never notice it if you were floating there. Voyager 2 turned that region from an artist's impression into a real measured shock front with numbers attached. But if the bulk flow slows and heats, what happens to the really energetic particles, the ones already moving much faster than the average? As Voyager 1 and Voyager 2 approached the termination shock, they saw something else go up, the intensity of anomalous cosmic rays, a specific class of energetic particles that start as neutral atoms drifting in from interstellar space, get ionized, picked up by the solar wind, and then boosted in energy near the shock. These particles don't just pass through once, they bounce back and forth across the shock on tangled magnetic field lines, gaining energy every time they cross the moving barrier. A process called diffusive shock acceleration. The data showed clear increases in these energetic particles as the spacecraft neared the shock, then changes as they crossed and moved beyond. That pattern matches what you expect from a large-scale particle accelerator, one powered not by magnets in a ring on Earth, but by the sun's outflow slamming into the galaxy. The termination shock is not just a speed bump in the wind, it's a giant engine that shapes the spectrum of particles streaming through the outer heliosphere. Particles that can later leak inward and contribute to the radiation environment near Earth and the other planets. So why does any of this matter for the big picture of the heliosphere, for how strong our shield really is? Once you know roughly where the termination shock sits in different directions and how strong the shock is, you can back out the pressure of the solar wind at those distances and compare it to the pressure of the surrounding interstellar medium. Pressure here includes not just the particle motion but also the magnetic pressure and the contribution from energetic particles like cosmic rays. If the shock is closer in on one side, it tells you the external pressure is higher in that direction, or the solar wind is weaker there, or both. The fact that Voyager 1 hit the shock around 94 astronomical units, and Voyager 2 at about 83.6 astronomical units, already shows that the sun's bubble is not symmetrical. The solar wind's bubble pressure is being pushed back harder in some directions than others. When you combine that with other missions that image energetic neutral atoms from afar, you get the first solid constraints on the overall size and shape of the heliosphere. It's lopsided, it responds to the galaxy around it, it's not an isolated system. Those two crossings turned the termination shock from a guess into a measured three-dimensional surface. And that sets up the next step in the story, because once you cross the shock, you're not at the final edge yet. Between the termination shock and the heliopause lies the Heliosheath, a huge, hot, turbulent layer where the solar wind is slowed, compressed, and stirred up on scales of billions of kilometers. If the first wall is already bent and uneven, what does it feel like to travel through that entire chaotic outer shell, where the sun's shield is doing most of its work and the galaxy is pushing back hardest? So after you slam through the termination shock, does space finally calm down, or does it get worse? For Voyager, it got rougher. Beyond that first wall, the spacecraft entered the Heliosheath, a region of slowed, heated solar wind that's roughly 20 to 40 astronomical units thick. tens of billions of kilometers, tens of billions of miles of disturbed plasma. Inside the inner heliosphere, the solar wind was racing outward at hundreds of kilometers per second. In the Heliosheath, that flow speed dropped and the temperature jumped into the hundreds of thousands of Kelvin. It's still a very thin gas by everyday standards, but compared to the inner wind, this is a hot, compressed layer where everything is more violent. You're not coasting through empty space, you're ploughing through the sun's outer shock absorber. Here's the first surprise: the termination shock itself doesn't sit still. Voyager 2 showed that directly. It didn't just cross one neat, fixed boundary and leave it behind. Around 2007, and the years around that crossing, it saw several shock-like transitions, small jumps in speed, density and magnetic field that look like the spacecraft crossing the shock multiple times. That means the shock was moving, sometimes inward, sometimes outward as the solar wind pressure changed. When the sun is more active, it throws out more material and magnetic field, the solar wind pressure rises, and the shock is pushed farther into interstellar space. When the sun quiets down, the pressure drops, and the whole boundary system can move inward. Now scale that motion. Moving the termination shock by just a few astronomical units means shifting it by hundreds of millions of kilometers, hundreds of millions of miles. Over the 11-year solar cycle, the outer edge of the solar system literally breathes in and out by that amount. Voyager 2's yo-yo ride across the shock is your direct evidence that this is not a rigid shell. It's a flexible border reacting to solar activity. That breathing then ripples outward through the whole Heliosheath and eventually affects the true edge at the heliopause. So what fills this layer while Voyager is riding through it for years? One of the clearest stories comes from the particles. Inside the inner heliosphere, lower energy particles from the sun dominate. Things like solar energetic particles from flares and the normal solar wind population. As Voyager moved deeper into the Heliosheath, it watched those lower energy, solar origin particles slowly decline in intensity. At the same time, higher energy galactic cosmic rays from outside the heliosphere kept creeping upward. It's like watching traffic from two highways merging, one coming from the sun, one coming from the galaxy. This slow trade-off is more than a nice plot, it's a countdown. The farther out you go in the Heliosheath, the more the sun's contribution fades and the more the raw galactic background shows through. When the galactic component stops rising and levels off and the solar component drops sharply, you're close to the heliopause. Voyager 1 and 2 saw that gradual change play out over several astronomical units, so by the time the final jump happened at the heliopause, scientists already knew they were near the real border just from that particle traffic pattern. But particles don't just move through a static background, they follow magnetic fields, and those fields in the Heliosheath are a mess. The magnetic field instruments on both Voyagers recorded a pattern that is anything but smooth. The field strength shows sudden jumps and drops, the direction swings around, sometimes slowly, sometimes abruptly, and small shock structures appear and merge. The absolute numbers sound tiny. Typical Heliosheath fields are fractions of a nanotesla, much less than a millionth of Earth's surface field, but on scales of billions of kilometers, that is more than enough to control the motion of charged particles. Charged particles spiral around magnetic field lines. If the field direction twists, their paths twist. If the field strength changes, their spiral radius changes. In a region where the field is constantly fluctuating, particles scatter, get trapped or leak through, depending on their energy and the local geometry. The Heliosheath is where this tangled magnetic environment does most of the work, shaping which cosmic rays get in and which get kept out. It's not just noise, it is the structure that determines how effective the heliosphere is as a shield. So why should you care about all this chaos when you're sitting safely on Earth, one astronomical unit from the sun? Because the Heliosheath is where most of the heliosphere's shielding power actually lives. The thickness of this region, its turbulence level, and how it responds to changes in solar activity all feed into one key outcome: how many high-energy galactic cosmic rays make it through to the inner solar system? If the Heliosheath is thicker or more turbulent, it can scatter and moderate more particles before they ever get near Earth's orbit. If it thins or becomes less effective, more of those particles get through. This matters for Earth's atmosphere, for climate studies, and very directly for radiation exposure. On the International Space Station, astronauts already deal with higher radiation levels than on the ground, because Earth's magnetic field and atmosphere only block so much. If you send crews on long-duration missions to the outer planets, or eventually beyond the heliopause, they will see an even higher background of cosmic rays. Voyager's measurements in the Heliosheath let you quantify how that background ramps up as you approach the edge. That tells you what kind of shielding you would need on an interstellar ship, how thick your walls have to be, what materials you might use, whether you want extra water or hydrogen-rich plastics to soak up those particles. So the Heliosheath isn't just some distant curiosity at 80, 100, 120 astronomical units. It's the outer engine room of the Sun's protection system. It responds to the 11-year solar cycle, it shapes the cosmic ray flux that reaches Earth, and it sets the starting conditions for any spacecraft that dares to cross into true interstellar space. Voyager turned it from a vague outer region into a mapped, measured buffer zone with moving boundaries and real, changing numbers. But even after years of fighting through that hot, turbulent layer, Voyager still wasn't out. The solar wind, even slowed and heated, still existed around it. The galactic cosmic ray intensity was still climbing. So the next question was simple and brutal. If this much structure is sitting between the termination shock and the outer border, what happens right at that final line, at the heliopause itself, when the Sun's influence finally drops away and the interstellar medium takes over completely? How do you know you've finally left the Sun's bubble when there's no signpost? Just instruments counting particles and measuring tiny magnetic fields. On August 25, 2012, Voyager 1 was about 122 astronomical units from the Sun, roughly 18 billion kilometers out, about 11 billion miles. For years, its detectors had seen a slow trend, lower energy particles from the Sun drifting down, higher energy galactic cosmic rays drifting up. Then, over a short time, everything changed. The lower energy solar particles plunged, and at the same moment the galactic cosmic rays spiked. Two curves that had been sliding gradually suddenly shot away from each other. That solar down galactic up signature is exactly what you expect when you cross the heliopause, moving from a region dominated by the Sun's particles into one dominated by the galaxy. That looks like the edge, but a plot alone is not enough. A particle flip tells you the character of the radiation has changed. It doesn't tell you what the surrounding gas actually is. The obvious next question is, can you measure how dense the plasma is out there and check if it matches interstellar predictions, rather than heliospheric ones? Here the mission ran into a big limitation. Voyager 1's main plasma instrument had failed back at Jupiter, so it could no longer directly measure the solar wind flow. The only tool left for density was the plasma wave detector, which can't see electrons one by one, but can hear the plasma vibrate when something disturbs it. About a year after the 2012 particle cliff, a major solar eruption, a coronal mass ejection, launched a shockwave outward. More than a year later, that shock finally reached Voyager 1, compressed the plasma around it and set it ringing. Those vibrations showed up as a radio tone in the data, about 2.6 kHz. The key point is simple. The natural frequency of that tone depends on how many electrons are packed into each cubic centimetre. Higher frequency means higher density. When scientists converted that 2.6 kHz signal into a number, they got an electron density of about 0.08 particles per cubic centimetre. In the outer heliosphere, you expect something like 0.002. So Voyager was now sitting in plasma roughly 40 to 80 times denser than the heliospheric value, right in the range long predicted for the local interstellar medium. Put those two results together. The particle mix has flipped from mostly solar to mostly galactic, and the plasma density has jumped from a heliospheric value to an interstellar one. That combination is the clear physical sign that Voyager 1 is no longer in the sun's wind, but in the surrounding galactic gas. There was still one big expectation hanging over this moment. Before the crossing, many models predicted that the magnetic field direction should swing sharply at the heliopause. Inside the heliosphere, the field follows the sun's field, wrapped into a spiral by rotation. Outside, the local interstellar field should point along a different direction in space. So the simple picture said, once you cross the boundary, the field direction should jump like a compass needle suddenly snapping to a new north. Voyager 1 did not see that clean jump. Its magnetometer recorded a step up in field strength, which fits the idea of a slightly stronger interstellar field plus compressed plasma. But the direction of the field changed only a little. On the outside, it pointed surprisingly close to where it had pointed on the inside. That mismatch between theory and data triggered an argument. One camp suggested Voyager had entered a magnetic highway region, where field lines from inside and outside are linked, letting particles leak through while the field direction stays similar. Another camp pointed out that the interstellar field direction was not well known, so it was entirely possible that, by chance, it really did line up near the heliospheric field in Voyager's sector. For a while, that missing magnetic flip kept the verdict cautious. The particle and density data said interstellar, but the field direction did not. The way out was to use all the data together. Teams built global models of the heliosphere and heliopause, then tested them against years of Voyager measurements. More solar storms sent shocks outward. Each time one reached Voyager, the plasma rang again, and each time the inferred density stayed in the same interstellar range, not the heliospheric one. By September 2013, the weight of evidence was strong enough that NASA and the wider community made the call. Voyager 1 is in interstellar space. More precisely, it is in the local interstellar medium just beyond the heliopause. It has not left the solar system in a gravitational sense. The sun's gravity still dominates out to the distant Oort cloud, far beyond Voyager's position. But in terms of the sun's wind-blown plasma bubble, Voyager 1 has crossed the outer boundary. That is the definition of edge that matters for radiation, space weather, and the cosmic environment around us. That brings up the scale question that really puts this in perspective. How fast do you have to go to reach that edge? And how large is 122 astronomical units? Voyager 1 is one of the fastest spacecraft ever launched. It cruises at about 17 kilometers per second relative to the Sun, roughly 38,000 miles per hour. At that speed, you could cross the continental United States in under 5 minutes. And yet, even moving that fast, it took 35 years to get from Earth's orbit out to the heliopause. That contrast is what makes the size of the heliosphere sink in. A probe moving at 17 kilometers per second, boosted by gravity assists from giant planets, still needs decades just to reach the edge of the sun's wind. From where Voyager 1 is now, it will still take tens of thousands of years just to reach the inner Oort cloud. So at this point you have one spacecraft racing at 17 kilometers per second, sampling the interstellar medium just beyond the heliopause along a single narrow path. It has given you the first hard numbers for particle populations, plasma density, and magnetic field right outside the sun's bubble. The obvious next tension point is this: did we just get lucky with one clean crossing, or is that picture truly representative? To test the shape and behaviour of the heliopause, and to see how stable that edge really is, you need a second crossing in a different direction, under different solar conditions. So was Voyager 1 just a lucky shot through a weird patch of space? Or does its story hold up when you check the edge of the heliosphere from another direction entirely? That's the question Voyager 2 was about to answer. On November the 5th, 2018, Voyager 2 reached a distance of about 119.7 astronomical units from the Sun, roughly 17.9 billion kilometers, about 11.1 billion miles. It was coming out below the plane of the planets, in the opposite hemisphere from Voyager 1. And right there, just a couple of astronomical units closer in than Voyager 1's crossing, it saw the same kind of sharp change in space environment, the same kind of border. Two probes, different paths, different solar conditions, but almost the same heliopause distance. That near match is your first big hint that the heliopause isn't some huge comet-like tail stretching way off in one direction. It's closer to a rounded shell, distorted but not wildly lopsided. But there was still a missing piece from Voyager 1's crossing that people had argued about for years. Could we see the solar wind itself stop in real time at the heliopause? This is where Voyager 2 is crucial. Its plasma instrument, the one that directly measures the speed, density and temperature of the flowing gas, was still working in 2018. As Voyager 2 approached 119.7 astronomical units, that instrument watched the solar wind speed fall. Inside the Heliosheath, the flow was still moving outward, slower than in the inner heliosphere but clearly detectable. At the crossing, that speed dropped towards zero relative to the spacecraft. In simple language, the outward wind disappeared, replaced by a different, more static plasma environment. At the same time, the measured plasma density changed sharply. On the inside, densities matched the expectations for the hot, low-density Heliosheath. On the outside, the plasma became denser, more in line with the local interstellar medium. Unlike Voyager 1, which had to wait for a solar shock to pass by and ring the plasma like a bell, Voyager 2 saw the local change directly, moment by moment, as it stepped across the boundary. That direct confirmation closed a big gap. It showed that the heliopause is exactly what you expect physically, a place where the sun's wind slows to nearly zero and the external medium takes over. Then comes the test you really care about for radiation and shielding. Do the particles tell the same story the plasma does? Voyager 2's energetic particle detectors saw a pattern that echoed Voyager 1, but with cleaner timing and some differences in detail. As it approached the heliopause, the intensity of lower energy particles from the Sun dropped steeply. At almost the same time, the intensity of higher energy galactic cosmic rays rose. There were small differences. Some energy ranges changed earlier or later than others, but the core picture was the same: solar origin particles down, galactic particles up across a narrow radial distance. Those timing differences matter. They tell you about how thick the boundary is, how tangled the magnetic field is, and how easily particles of different energies can cross. But the key point is simple: independent instruments on a second spacecraft, in a different part of the Heliosphere, hit a surface where the particle populations flip in the same basic way. The heliopause is no longer one dramatic Voyager 1 plot, it's a repeatable measured boundary. So with two edges in two directions, what does that say about the global shape of the Heliosphere? If you take Voyager 1's crossing at around 122 to 122.6 astronomical units, and Voyager 2's crossing at about 119.7 astronomical units, and you combine that with models of the solar wind flow and the interstellar medium, you can reconstruct a three-dimensional picture of the heliopause. The result is not a long comet tail with a tiny head like older textbook figures suggested. Instead, you get something much more compact and almost bubble-like, with only a modest trailing region. The surface is not perfectly smooth. It has dents and wrinkles, shaped by the direction of the interstellar magnetic field and the flow of interstellar gas past the Sun. In some directions, the heliopause is pushed in a bit closer, in others it can extend slightly farther. But the headline is clear. For the first time, humanity has two real data points on the shape of its own protective bubble. Every global model now has to match those crossing distances and the conditions at each spacecraft, or it's wrong. But the shape alone doesn't tell you how hard the galaxy is pushing on that bubble. That comes from pressure, from how much force per area the external medium applies. Voyager 2's detailed plasma measurements, combined with its particle and magnetic field data, let scientists estimate the total pressure outside the heliopause, including contributions from the thermal motions of particles, the interstellar magnetic field, and the local cosmic ray population. The result came in higher than many earlier models had assumed. A higher external pressure means the Sun's wind has to work harder to hold its ground. For a given solar wind output, a stronger outside push shrinks the heliosphere, compressing it closer to the Sun. That in turn changes how effective it is at shielding the planets. A more compact, more heavily squashed heliosphere can still block a lot of cosmic rays, but its structure is different from what you'd get in a gentler environment. The exact balance sets which energies get deflected and which energies leak in. That's not an abstract tweak to a simulation. Cosmic rays affect atmospheric chemistry, radiation doses for astronauts, and long-term exposure for electronics. If the local interstellar medium is pushing harder than we thought, it means the sun's protective bubble is under more stress, and that the background level of galactic radiation in the inner solar system may be different from what older models predicted. As we send spacecraft farther out, and as we think about eventual crewed missions that go beyond the Heliosphere, those numbers move from interesting to mandatory input. So now you have two probes in interstellar space, in different directions, both showing a similar heliopause distance, both confirming that the sun's bubble is more compact and more stressed by the galaxy than some classic pictures suggested. That naturally leads to the next, sharper question. If the external pressure is higher and the edge is closer than we thought, exactly how dense is the interstellar plasma out there? And how can you measure that density with a 1970s spacecraft sitting 18 billion kilometers from home? How do you turn silence in deep space into a number for how many electrons are around your spacecraft when you can't count a single one directly? That's what Voyager had to solve. Its plasma wave instrument doesn't see individual particles, it listens for how the plasma vibrates when something hits it. Think of the plasma as a very thin charged gas. When a strong disturbance, like a shock from a solar storm, passes through, it jolts the electrons. They slosh back and forth against the positive ions, and that motion produces a natural oscillation, a kind of radio frequency ringing. The key detail is simple. The higher the electron density, the higher the natural frequency of that ringing. So if you can measure the tone, you can infer the density. Voyager 1's plasma wave instrument picked up a tone around a few thousand cycles per second, roughly 2.6 kilohertz, after one of those shocks from a major solar eruption reached it beyond the heliopause. From that frequency, scientists worked out that the electron density was about 0.08 electrons per cubic centimetre in the seek of space around the spacecraft. That number is not just some random value. Long before Voyager ever got near the heliopause, models of the local interstellar medium, based on starlight absorption and other data, predicted that the plasma density near the Sun's neighbourhood in the galaxy should be around that level, a few hundredths of a particle per cubic centimetre. So when Voyager 1's hearing gave 0.08 per cubic centimetre, it was a strong independent confirmation this is interstellar plasma, not the Sun's wind. But how big a jump is that really, going from the outer heliosphere to the local interstellar medium? Inside the heliosphere, especially in the outer regions before the heliopause, typical electron densities are around 0.002 particles per cubic centimetre. That is already incredibly tenuous. A single cubic centimetre the size of a sugar cube would contain only a couple of thousand electrons. When Voyager 1 stepped outside, that density went up to about 0.08 per cubic centimetre. Depending on which exact value you compare to, that's roughly a 40 to 80 times increase. You should keep the absolute scale in mind. Even after that jump, the interstellar medium is still an extreme vacuum by everyday standards, thousands of trillions of times thinner than the air you breathe at sea level. If you somehow scooped up a volume of interstellar gas as large as a room, it would contain only about as many particles as the tiny puff of air on Earth. But for plasma physics, for how waves move, how shocks form, how magnetic fields interact, that change from 0.002 to 0.08 is huge. It changes how fast disturbances travel, how effectively particles can be scattered, and how the sun's boundary reacts to pressure from outside. So once you know the density, the next questions are obvious. How hot is this gas? And how fast does sound move through it? Voyager doesn't have a thermometer you can stick into the plasma, but with a known density and measured magnetic field, plus models of how the heliosphere and interstellar medium must balance at the boundary, you can estimate the temperature. The results point to values of tens of thousands of Kelvin, think in the range of 20,000 to maybe 50,000 Kelvin, depending on the exact mix of components. Again, that sounds extreme, but temperature in a plasma is a measure of average particle energy, not something you feel as heat the way you feel a hot stove. The gas is so thin that even at tens of thousands of Kelvin it would not burn you. There just aren't enough particles. A better way to think about it is to compare it to something familiar in terms of energy per particle, like the exhaust of a jet engine, but instead of being crammed into a tight nozzle, that energy is stretched across tens of billions of kilometers. From that temperature and density, and with the local magnetic field strength around half a nanotesla or so, you can also estimate the speed at which pressure waves, the equivalent of sound waves, move through the interstellar plasma. You get values of tens of kilometers per second, say 20 to 50 kilometers per second, around 40 to 100,000 miles per hour. That sound speed is what defines whether the solar wind is supersonic or subsonic relative to the surrounding medium, and helps set the structure of shocks and waves around the heliopause. Now, here's the catch that makes this harder than just turn the instrument on and read the value. Voyager's plasma wave detector only gets clear density measurements when something strong shakes the plasma. Under quiet conditions, the background noise can be low and diffuse, and you don't get a clean tone. To get a sharp reading, you need a major disturbance, usually a coronal mass ejection, a big solar eruption that launches a huge cloud of magnetized plasma outwards at hundreds of kilometers per second. When one of those eruptions leaves the sun, we can watch it with spacecraft near Earth and with solar observatories. Then you wait. It travels through the inner heliosphere in days, past Jupiter in weeks, through the outer heliosphere in months, and only after more than a year does it finally reach Voyager out near or beyond the heliopause, at over 100 astronomical units. When it does, it compresses the plasma around the spacecraft and triggers that ringing at a specific frequency. The delay between the eruption and the signal in Voyager's data tells you how long it takes solar weather to cross the entire heliosphere and hit the interstellar medium just outside. Each of those events gives you a snapshot of the density at a particular time and distance. Over the years, several shocks have passed Voyager 1, and each one has produced plasma wave tones consistent with the same interstellar density range, reinforcing the idea that the spacecraft is firmly in the local interstellar medium, not just in some odd transition layer. At the same time, those events remind you that the heliopause and the space just beyond it are not static. Solar storms leave their mark out there, even after travelling for more than a year across tens of billions of kilometres. So now you have density, you have a handle on temperature and sound speed, and you have a clock showing how long the sun's eruptions take to punch through its own bubble and disturb the galactic environment just outside. That sets the physical background for the next question that directly matters for life and technology inside the heliosphere. Given this density and this boundary behaviour, how much of the galaxy's high-energy particle rain actually gets through? And how much does the heliosphere really cut down the cosmic ray storm you would face if you stepped completely outside? How do you actually see the heliosphere's shield failing as you move toward the edge? Not in theory, but in numbers ticking up on a detector. Between about 2009 and 2012, Voyager 1 gave a very clear answer. Its cosmic ray instruments watched the intensity of galactic cosmic rays, the high-energy particles from the rest of the galaxy, creep upward, slowly but steadily. Over those few years, the count went up by about 25%. No drama, just a continuous rise as the spacecraft moved outward through the Heliosheath, where the sun's influence is already weaker, and the galaxy's contribution starts to leak through more easily. Then, as Voyager 1 got close to the heliopause in 2012, that slow climb turned into a spike. In one short interval, the galactic cosmic ray intensity jumped by about 5% in a single week, then nearly 10% in about a month. At the same time, the intensity of lower energy particles from the sun dropped sharply. You're seeing the shield thin out in real time, the last layers of heliospheric turbulence losing control over the incoming particle flux. That 1-2 pattern, a long slow rise followed by a sudden jump near the final boundary, is the clearest way you can watch the heliosphere's protection turn off along that path. Now, these are not just any particles. Voyager's cosmic ray instruments, built in the 1970s, were designed to measure energy spectra for particles over a wide range, including down to a few million electron volts per nucleon and up into much higher energies. Those particles have been accelerated in violent events, like supernova remnants and other shock fronts scattered across the Milky Way. They travel at significant fractions of the speed of light, and when they hit matter, they can ionize atoms, damage DNA, and flip bits in electronics. In other words, these are the bullets the Heliosphere is catching for us. The impressive part is that those detectors, with 1970s electronics and design, were still good enough to separate out the contributions from different energy bands decades later. Inside the Heliosphere, the intensity in certain ranges is held down by solar modulation, the combined effect of the solar wind and magnetic field scattering and decelerating cosmic rays. Once Voyager 1 stepped outside the heliopause, that modulation dropped away. The flux of high-energy particles increased to a higher, relatively stable level. That plateau is your background, the true galactic cosmic ray environment in our local patch of the Milky Way. When you compare the inside and outside levels, you get a direct experimental measure of how much the Heliosphere is cutting down the flux at those energies. It's not a perfect shield, especially at the highest energies, but it clearly reduces the number of particles that reach Earth's orbit. The next question is whether that profile, that gradual climb and sudden jump in the north, is some special feature of Voyager 1's trajectory, or a general property of the heliopause. Voyager 2, heading out in the opposite hemisphere and crossing in 2018, gave you the second view. As it approached its heliopause crossing at about 119.7 astronomical units, its instruments saw another pattern of rising galactic particles and falling solar particles. The details were not identical. Some energy channels responded at slightly different distances. The slope of the rise and the width of the transition were not exactly the same. But the big picture held move outward. Solar origin particles go down, galactic cosmic rays go up. Then, near the boundary, you get a sharper change. Those differences are not noise, they carry information. They tell you that the transition region has some finite thickness, not a razor-thin wall, and that this thickness and structure depend on local magnetic field geometry. In the southern hemisphere, along Voyager 2's track, the field lines and turbulence pattern are not a carbon copy of Voyager 1's northern path. That changes how easily different energy particles can cross, and how quickly the spectrum shifts from heliospheric to interstellar. Comparing the two gives you constraints on how the heliopause looks and behaves in 3 dimensions, instead of along a single line. The key practical question, though, is simple. If you're sitting on Earth, inside this bubble, how much protection are you actually getting from all of this? The answer comes from models that use Voyager's inside versus outside measurements as anchors. For some energy ranges, especially in the tens to hundreds of millions of electron volts, the heliosphere can reduce the incoming cosmic ray flux by factors of around 2 or more, depending on the phase of the solar cycle. During solar maximum, when the sun is more active and the heliospheric magnetic field is more tangled, modulation can be stronger. During solar minimum, the shield weakens somewhat. Translating that into human terms, if you took a spacecraft from the inner solar system and pushed it outside the heliosphere, kept the same shielding and the same trajectory otherwise, the crew would see something like up to about double the galactic cosmic ray dose in some energy bands compared to what they would get in interplanetary space near Earth's orbit. Exact numbers depend on shielding design and timing, but the scale is clear. Leaving the heliosphere is not a small step in radiation terms. For electronics, that increase means more single-event upsets, more bit flips, more need for redundancy and error correction. For future human crews on decades-long missions through interstellar space, it means thicker shielding, smarter material choices, and serious attention to how much total dose a person can safely absorb over a lifetime. You can't hand-wave that away with vague, "we'll deal with it later" statements when Voyager has already shown you the baseline environment. So from the slow 25% rise in galactic cosmic rays over several years, to the sharp 5 to 10% jump right at the heliopause, from the 1970s instrument still counting particles from ancient supernovae to the comparison between two hemispheres, you now have a quantitative picture of how much the galaxy really gets through the sun's shield and how much the shield pushes back. That leads straight into the next puzzle though. If the heliosphere can modulate cosmic rays by that much, a lot of that power must be coming from its magnetic field structure. But when Voyager crossed the edge, the one thing scientists expected most from the field, a clear directional flip, mostly didn't happen. So what is actually going on with the magnetism at the border? And why did the compass not behave the way the model said it should? You've seen how the particle counts and plasma density tell a clear story at the edge, so the next thing you'd expect is for the magnetic field to back that up with a clean, obvious flip. Inside the heliosphere, the field is basically the sun's magnetic field, dragged outward by the solar wind and twisted into a spiral shape as the sun rotates. Outside the field should be the local interstellar magnetic field, set by the galaxy with its own direction. The simple prediction was, cross the heliopause, and the magnetic field direction should swing by a large angle from heliospheric to interstellar, a neat, unmistakable compass jump. Voyager 1 did not give you that neat jump. As it crossed the heliopause region in 2012, the magnetometer saw the field strength go up, which makes sense. The plasma outside is denser, and the external field is slightly stronger. But the direction, the actual orientation of that field vector in space shifted only modestly. The field outside pointed surprisingly close to the direction it had inside, not identical, but not the dramatic flip many models had drawn. So now you had a weird combination, particles and density that screamed interstellar medium, and a magnetic direction that looked almost heliospheric. That mismatch caused real confusion. One group looked at the small directional change and said, maybe Voyager 1 is still inside in some strange outer layer of the heliosphere, and has not fully crossed the heliopause. Another group pointed at the particle and density data and said, the spacecraft is out, and the field behavior just means our mental picture of the boundary is too simple. The compass didn't flip the way people expected, so either the edge is more complicated, or the interstellar field near the sun happens to line up more closely with the heliospheric field than we thought. To describe what Voyager 1 found right after the crossing, scientists introduced a new term, the magnetic highway. In that region, solar origin particles at certain energies dropped, galactic cosmic rays moved more freely, and the magnetic field became more ordered, with less turbulence than in the inner Heliosheath. The idea was that field lines in this zone might be connected to both sides, to the sun's field on one end, to the interstellar field on the other. That kind of connection would let galactic cosmic rays stream in along those lines, while allowing some solar particles to leak out, even before you reach fully unperturbed interstellar space. This magnetic highway picture backs up an important idea. The heliopause is not a perfect sharp wall. It's a contact region, a place where magnetic fields from the sun and the galaxy interact, twist, reconnect, and form mixed structures. In plasma physics, when two magnetic systems press against each other, they often reconnect, breaking and rejoining field lines in new combinations. At the heliopause, that process can create channels where particles cross more easily than a simple barrier model would allow. So instead of thinking inside then instant outside, you think inside then a thin but structured interface, then outside. That still left the big question though. Did the lack of a big field flip mean the interstellar field itself was pointing differently than expected? Or did it mean Voyager 1 was in some kind of layered transition, not fully out? This is where later global simulations plus Voyager 2's data helped straighten things out. When researchers built more detailed magneto-hydrodynamic models of the heliosphere, including the sun's motion through the local interstellar medium and a realistic interstellar field, they found something interesting. It is entirely possible for the interstellar magnetic field direction, near the nose of the heliosphere where Voyager 1 crossed, to lie fairly close to the direction of the stretched heliospheric field in that same region. In other words, the field direction outside doesn't have to be wildly different from the field direction inside, especially along that specific trajectory. The fact that Voyager 1 saw only a modest change then becomes a constraint on the geometry, not a contradiction. It says, whatever the true interstellar field direction is around the Sun, it must be such that, after draping and compression around the heliosphere, the field near Voyager 1's crossing point ends up close to the Parker spiral direction it had just inside the boundary. Voyager 2's crossing in 2018 added another piece. Its magnetometer also saw the field strength step up as it crossed the heliopause, and the direction outside settled into a pattern consistent with a draped interstellar field, not wildly off from Voyager 1's result when you account for the different location and geometry. When you put both datasets into the same global models, you can solve for a local interstellar magnetic field strength of around half a nanotesla, with a direction that is tilted relative to the incoming interstellar gas flow by some tens of degrees, but still able to match the modest directional changes seen at both spacecraft. Half a nanotesla sounds almost meaningless at first glance. To give you a scale, Earth's magnetic field at the surface is about 50,000 nanotesla. A simple fridge magnet can be tens of millions of nanotesla. So you're talking about a field that is weaker than a fridge magnet by a factor of many millions, and weaker than Earth's field by a factor of roughly 100,000. It is very easy to hear 0.5 nanotesla and think, that can't matter. But you need to combine that strength with the size of the region it fills. The heliosphere itself extends out to roughly 100 to 120 astronomical units in the nose direction, and the interstellar field that surrounds it continues across distances of tens of thousands of astronomical units and beyond through the local galactic environment. Charged particles like cosmic ray protons and electrons feel the magnetic field through their electric charge, and their paths bend according to both field strength and the size of their orbit around a field line. Over such vast distances, even a very weak field can steer their trajectories by huge angles, scatter them or trap them in particular regions. That half nanotesla field is also what pushes on the Sun's bubble, shapes the overall outer line of the heliosphere, and decides how strongly the nose is squashed and how any tail region is formed. It influences how neutral atoms and small dust grains flow into the solar system, and how they get ionized and picked up by the solar wind. It sets the boundary conditions for space weather on interstellar scales, not just around Earth. So, from a small directional non-event in Voyager 1's magnetometer data, you end up rewriting how you think about the heliopause. The compass not flipping violently does not mean there is no edge. It means the interstellar field geometry near the Sun is more subtle and more closely aligned with the heliospheric field in that region than early cartoons suggested. And that tiny half-nanotesla field spread over tens of thousands of astronomical units quietly shapes the size, the shape, and the shielding power of the entire heliosphere. Once you accept that, another question pushes in. If the magnetic field outside is really doing that much work, then maybe the old picture of the heliosphere as a long comet-like tail stretching far behind the Sun is wrong too. With two crossings, new density numbers, and a better handle on the external field, what does the global shape of our bubble actually look like? And how exposed does that shape leave us to the galaxy around us? How wrong was the picture you grew up with? The one that showed the solar system sailing through the galaxy with a long, comet-like tail stretching out behind it. For a long time, that cartoon dominated textbooks, the Sun at the nose, and a huge tail of heliospheric plasma trailing for hundreds or thousands of astronomical units downwind. It felt intuitive. The Sun moves through the local interstellar medium, so its bubble should stream out into a long wake. But when you combine the actual Voyager termination shock distances, the heliopause crossings, and sky maps from missions like IBEX that image energetic neutral atoms coming from the outer heliosphere, that simple comet tail stops working. The data point towards something more compact and surprisingly rounded, closer to a squashed bubble, or even a croissant-like shape with folded lobes, and only a short distorted tail region rather than a gigantic streamer. So how do you actually measure a three-dimensional shape when you only have a couple of spacecraft and a few all-sky images to work with? The first handle comes from the termination shock. Voyager 1 and Voyager 2 each crossed the shock once cleanly, and Voyager 2 saw it shift a few times as the boundary moved with solar activity. In total, you get 4 meaningful points where the shock was sampled in different directions and at different times. When you combine those with IBEX maps, which show where energetic neutral atoms are coming from as the solar wind and interstellar medium interact, you can fit a global model. Those models say the termination shock is roughly close to a spherical surface with a radius of about 117 astronomical units, but the Sun is not sitting perfectly at the centre. The sphere is offset by tens of astronomical units in various directions. That offset is the direct signature of the interstellar wind and magnetic field pushing harder on some sides than others, in the direction of motion through the galaxy. And along the interstellar magnetic field, the shock surface is squeezed in. In other directions, it can bulge out slightly. When you plot those inferred offsets, you don't see a long simple tail, you see a bubble that's being squeezed and twisted, with any tail region being short and complex. If the termination shock is only the first surface, what about the outer one, the heliopause itself? Voyager 1 and Voyager 2 gave the first in situ readings, and those readings tell you something important about how sharp that outer skin really is. In many early diagrams, the heliopause was drawn as a neat, thin line, like a border on a map. The real data are messier. Voyager 1's particle and field instrument saw changes over a range of distances around its 2012 crossing, with some parameters jumping fast, others changing over a fraction of an astronomical unit, and some still evolving over a couple of astronomical units beyond. Voyager 2's crossing shows a similar pattern, with a steep change in solar wind speed and particle populations over a relatively narrow radial range, but still not zero thickness. Depending on which quantity you use to define inside versus outside, particle spectra, plasma density, magnetic structure, you get slightly different widths. The conclusion is, the heliopause is not a razor-thin mathematical surface. It is a boundary layer, a region that might span from a fraction of an astronomical unit up to several astronomical units in radial extent. In distance terms, that's a skin millions to hundreds of millions of kilometers thick, more like a fuzzy transition shell than a clean, crisp wall. You might ask, if the boundary is that fuzzy and the global shape is that distorted, why should anyone on Earth care exactly what the outline looks like? The answer is, the shape of the Heliosphere controls which parts of the galaxy we're more exposed to and when. The nose of the Heliosphere points roughly into the direction of the Sun's motion through the local interstellar medium. If that nose region happens to point into a denser or more strongly magnetized patch of interstellar gas, the Heliosphere can be more compressed. A more compressed nose could change how many cosmic rays of different energies manage to penetrate to the inner solar system. Over millions of years, as the Sun orbits the Milky Way, it moves through different regions of the local interstellar cloud structure. Density and magnetic field strength can change. Each time they do, the pressure balance at the boundary shifts, the heliopause distance in various directions changes, and the overall shielding pattern for cosmic rays is altered. That means the flux of high-energy particles hitting Earth's atmosphere is not fixed over geological timescales. It can rise or fall as the heliosphere's shape inflates or deflates in response to the environment around it. There are studies that look at possible links between cosmic ray flux, cloud formation, and climate, as well as long-term impacts on biological evolution through radiation exposure. The details are still debated, but the key point for this story is straightforward. The heliosphere's geometry is not just a pretty plot for space physicists. It feeds directly into how much of the galaxy's radiation environment reaches the planets. When you change the bubble shape, you change the shielding pattern, even if Earth's orbit and the Sun's internal output stay the same. So you started with a simple cartoon, a huge comet-like tail and a neat boundary line, and ended up with a compact, offset, bubble-like heliosphere, wrapped in a boundary layer millions of kilometers thick, squeezed and dented by an interstellar magnetic field of only about half a nanotesla. That global structure decides where the termination shock sits, where the heliopause stands off, and how the nose and any tail interact with the incoming interstellar flow. Once you accept that the whole bubble is the product of a balance, a standoff, between the outflowing solar wind and the inflowing interstellar gas and field, the next question becomes unavoidable. Exactly how do those two winds, solar and interstellar, push against each other? How stable is that balance? And what happens when the sun's own output changes over time while the galaxy's pressure stays on? So what is the heliosphere really? If you strip it down to basics, it's a standoff between two winds. On one side you have the solar wind, plasma flowing out from the sun at hundreds of kilometers per second, a few 100,000 miles per hour, carrying the sun's magnetic field with it. On the other side you have the interstellar flow, gas and embedded magnetic fields streaming past the solar system at around 26 kilometers per second, roughly 58,000 miles per hour, as the sun moves through the local interstellar medium. Where those two flows meet, where their pressures balance, that's where Voyager took its key measurements. Inside that balance point, the solar wind dominates. Its dynamic pressure, plus its magnetic field, plus the pressure of energetic particles from the sun, are high enough to push back the surrounding medium. Outside that point, the interstellar gas and its magnetic field win. They push inward, compress the sun's bubble, and decide how far the heliopause can stand off from the star. The heliopause is literally the line where that tug-of-war ends in a draw. Voyager 1 and Voyager 2 crossed that line in different places at about 122 and 120 astronomical units and sent back the local conditions right at the front of the fight. Once you know those local conditions, you can ask a simple but powerful question. Given the external push, how big a bubble can our star afford? The answer comes from pressure balance. You add up the contributions to pressure outside the heliopause, the thermal motion of the interstellar plasma, the magnetic field pressure from that roughly 0.5 nanotesla field, and the pressure from galactic cosmic rays. Voyager's plasma measurements give you density estimates around 0.08 particles per cubic centimetre. The magnetic field instruments give you the field strength. The cosmic ray instruments give you particle fluxes that can be converted into an approximate pressure contribution. Sum all that, and you get the total external pressure that the heliosphere has to push against. On the inside, you know the solar wind's properties near Earth and can model how they fall off with distance. You can then solve for where the pressures match. That calculation reproduces a heliopause distance close to what Voyager measured, which is a good sign that the basic picture is right. It also lets you ask what-if questions. If the sun were blowing a weaker wind, say in a different phase of its long-term magnetic activity, the heliopause would move inward. If the sun were more active and its wind stronger, the bubble could expand outward. That is not just a thought experiment. The sun's output is not constant. Over the 11-year solar cycle, the solar wind pressure changes, and so does the structure of the heliospheric magnetic field. On longer timescales, over tens of thousands or millions of years, the average level of solar activity can drift. Each of those changes shifts the balance point with the interstellar flow. The size of the bubble is not a fixed number. It's a function of both solar output and external pressure. You've already seen one piece of evidence for that breathing effect, the multiple termination shock crossing seen by Voyager 2. That yo-yo in and out of the shock is the inner boundary of the outer region moving as the solar wind pressure changes. In the Heliosheath, Voyager saw density fluctuations and changing particle intensities that line up with variations in solar activity years earlier. Those are the internal parts of the bubble responding to the sun. Take that same logic to the outer edge. If the solar wind pressure goes up during a more active cycle, the heliopause can be pushed outward by a few astronomical units. If it goes down, the heliopause retreats inward. The changes are not huge in percentage terms, maybe a few percent of the total radius, but in absolute distance, moving the boundary by even 5 astronomical units means shifting it by about 750 million kilometers, close to 500 million miles. Over a few decades, the distance from Earth to the heliopause can change by that much. The bubble literally breathes, and Voyager flew through that moving boundary layer, while the Sun cycled through different activity states. There's another old prediction you have to deal with in this standoff picture, the idea of a strong bow shock ahead of the Heliosphere. In early models, the Sun was treated like a supersonic aircraft ploughing through air, with a sharp bow shock forming where the interstellar flow hit the Heliosphere head-on. That bow shock was drawn as a neat sharp surface upstream of the heliopause, where the interstellar gas would be abruptly heated and slowed. Voyager data, combined with observations from other missions, have largely taken that strong bow shock off the table. The key parameter is the Mach number of the interstellar flow, how fast it is compared to the speed at which pressure waves can travel through the interstellar plasma. With the densities and temperatures you now know from Voyager, the sound speed and magnetosonic speed in the local interstellar medium are high enough that the relative flow around 26 km per second is not strongly supersonic. That means a classic strong bow shock doesn't form. Instead, what you get is more like a bow wave, a region where the interstellar plasma and magnetic field are compressed and deflected gradually as they approach the heliosphere's nose, but without a sharp shock jump in all quantities. IBEX and other missions that sample energetic neutral atoms from this region see evidence of that smoother structure. Voyager itself, just beyond the heliopause, does not see signatures of a strong standing bow shock nearby. The solar system is not punching through the galaxy with a violent shock front like a supersonic jet. It's sliding through more gently, with a broad compressed region instead of a hard discontinuity. All of this leaves you with a clearer and more dynamic picture. The solar wind and interstellar wind collide at dozens to hundreds of kilometers per second. Their pressures balance at the heliopause, whose distance depends on both solar output and external conditions. The bubble expands and contracts over the solar cycle by several astronomical units, changing how far you have to travel from Earth to reach the edge. And the upstream region is shaped by a smooth bow wave, not a dramatic shock, meaning the transition from unperturbed interstellar medium to heliosphere-influenced medium is more gradual than early cartoons suggested. But even once you are outside that boundary, the story is not, we're in calm, featureless space now. Voyager's instruments keep seeing fluctuations in density, magnetic field, and cosmic ray intensities out in the interstellar medium itself. That tells you that the galaxy has its own kind of weather, with turbulence waves and old shock fronts passing by on scales of astronomical units. So the next problem is this. Once the Sun's direct influence fades a few astronomical units past the heliopause, what kind of interstellar weather is actually out there? And how does that turbulent environment affect any future spacecraft that try to follow Voyager into the deep beyond? How do you know you're really out in the galaxy's territory and not just in some calm, empty void? The surprising thing Voyager sees beyond the heliopause is that empty space is not steady at all. Once it crossed into interstellar space, the plasma wave and the magnetic field instruments kept picking up changes, not just tiny noise, but real variations in density and field strength of tens of % over distances of about a fraction of an astronomical unit to a few astronomical units. That means as Voyager moves billions of kilometers, the electron density goes up and down, the magnetic field strength wiggles, the direction shifts. This is interstellar turbulence, the same kind of messy, multi-scale behavior you see in fluids and in the solar wind, just in a much thinner medium and on huge length scales. So the obvious question is, what is stirring this stuff up if the Sun's wind is mostly out of the picture? One answer is, the galaxy itself has energy sources scattered everywhere. Supernova explosions, large-scale flows between different interstellar clouds, and shear from differential rotation all inject energy into the gas and magnetic field. That energy then cascades down to smaller scales as turbulence. Some of the waves and structures that Voyager detects out there could be fossil remnants of shocks from supernovae that happened millions of years ago, long since slowed and stretched out, but still leaving behind compressed regions and field enhancements. When Voyager records a bump in density or a kink in the magnetic field, it is sampling a tiny piece of that large-scale energy cascade. By looking at how often those bumps occur, what their sizes are and how strong they are, scientists can test models of interstellar turbulence not just with radio telescopes far away, but with a physical instrument sitting inside the medium. Each fluctuation is a clue about how energy injected at big scales, like hundreds of parsecs, turns into small-scale structure on astronomical unit scales. This leads to another important boundary question. How far does the sun's direct influence really extend once you are past the heliopause? Right at the boundary, you still see signatures of solar origin particles, fields, and shocks that have managed to cross or distort the interface. But as Voyager 1 and Voyager 2 move a few astronomical units farther out, those solar fingerprints fade. The particle populations settle into a steady interstellar spectrum, the plasma densities match the local interstellar medium value, and the magnetic field variations stop looking like extensions of the Heliosheath and start looking like generic interstellar turbulence. That transition zone, only a few astronomical units thick beyond the heliopause, effectively marks the practical reach of the sun's wind and magnetic field into the galaxy. Inside roughly 100 to 150 astronomical units, you're in a region where the solar wind and heliospheric magnetic field still dominate or strongly modify the environment. Beyond that, the interstellar medium's own structures take over. Gravity is different. The sun's gravity still controls comets in the Oort cloud out to tens of thousands of astronomical units, but in plasma and magnetic terms, the sun's direct control ends just outside the heliopause plus a small buffer. So what do these interstellar fluctuations mean for any future spacecraft that try to follow Voyager, or go even farther? Even though the densities and field strengths are small compared to what you see near Earth, they are not negligible. Variations in plasma density can scatter radio waves, changing how signals spread and occasionally causing scintillation, a kind of burrowing over long paths. Changes in magnetic field structure can bend the paths of charged particles, affecting how cosmic rays hit a spacecraft and how any active propulsion that relies on electromagnetic fields would behave. On top of that, small but persistent changes in plasma pressure and field tension can exert tiny forces on a spacecraft over long distances and times. The accelerations are tiny, but when you're trying to navigate over light day or light week scales with precise timing, those small forces can add up to measurable trajectory shifts. For communications, you need to account for how the interstellar plasma will disperse and delay radio signals over tens of billions of kilometers. For onboard systems, you need to expect that the radiation environment will not be perfectly uniform. Pockets with slightly higher or lower cosmic ray intensity will show up as you pass through different patches of turbulence. So the interstellar medium is not just a uniform background that you cruise through like a perfect vacuum. It has structure and variability on the scale of astronomical units, and Voyager has shown that clearly by logging density and field changes beyond the sun's direct reach. Any serious design for future interstellar probes has to treat that environment as weather you have to navigate and design around, not just a constant number in a spreadsheet. Once you see that, the next step is pretty direct. If the galaxy's own turbulence and the sun's fading influence shape the radiation and plasma environment out there, what does that mean for living things and hardware that might one day have to operate outside the Heliosphere for years at a time? And how does Voyager's data translate into actual safety numbers for humans and electronics beyond the sun's shield? So what does all this actually mean for a human body, in a ship, outside the sun's shield for years at a time? Voyager's data say very clearly, once you step beyond the heliosphere, the raw galactic radiation field is stronger across several important energy bands. That means more high-energy particles per square meter, per second, hitting whatever is out there. If you took a crude spacecraft with only modest shielding, the kind you might get away with in interplanetary space, and parked it where Voyager 1 is now, the annual radiation dose from galactic cosmic rays would likely jump to several times what astronauts see on the International Space Station. On the station, still under Earth's magnetic field and atmosphere, astronauts already take on a higher dose than people on the ground, and that is carefully monitored and limited. In deep interplanetary space, for example on the way to Mars, dose rates rise further because you lose Earth's magnetosphere but still sit inside the Heliosphere. Outside the Heliosphere, where Voyager is, you take away that last layer of protection. Voyager's inside versus outside particle counts let you put a number on that change. In some energy ranges you see roughly a factor of 2 increase, sometimes more, in the galactic cosmic ray flux. Turn that into dose, and you're talking about long-term exposures that would push right up against or past accepted lifetime limits if you did not build serious shielding into the spacecraft. That is the key habitability message. The heliosphere is not just a structure in a diagram, it's a radiation jacket for the entire solar system. It is a moving, breathing force field, not magical, just plasma and magnetic fields, but it cuts down a significant fraction of the charged particles that would otherwise hammer every atmosphere, every surface, every piece of electronics in our system. Before Voyager, you could talk about that in general terms. After Voyager, you can say, here is the dose difference between just inside the border and just outside it for different particle energies. That is the margin the jacket is giving you. For Earth, that jacket sits on top of Earth's own defences, its magnetic field and thick atmosphere. Those layers strip energy from incoming particles, force them into spirals, make them produce secondary showers high in the air instead of right at ground level. But if you remove the heliosphere entirely in a thought experiment, you would send a lot more high-energy primaries into that system. Voyager shows that the heliosphere knocks down some of those primaries before they even have the chance to meet Earth's magnetic field. Now take that logic and look outward at other stars. Every star with a steady wind will carve out its own bubble in the surrounding interstellar medium, an astrosphere instead of a heliosphere. If a star has a weak wind, or sits in a region of space where the external pressure is higher than what our Sun faces, its bubble will be smaller and more compressed. Planets in that system might still lie in a thermal habitable zone, where liquid water is possible, but the galactic cosmic ray environment at their orbits could be much harsher. The flux of high-energy particles hitting those atmospheres could be higher by factors of several compared to what Earth sees. That extra radiation can do a few things over time. It can drive more intense atmospheric chemistry, it can erode atmospheres more quickly if other protection is weak, and it can raise the surface and subsurface radiation levels that life has to tolerate. None of this instantly rules out habitability. Life is resilient and can hide underground or underwater, but it shifts the baseline. Voyager's numbers give you a template for what outside the bubble looks like in hard data, so when you model exoplanet systems, you can move a slider and say, if the astrosphere is this big, the cosmic ray environment looks roughly like this. If it's smaller, it looks more like Voyager's interstellar measurements. That directly feeds into how we refine habitable zone ideas. It's not just how far from the star so water is liquid, it's also how strong is the stellar wind, how big is the astrosphere, how much galactic radiation gets through. A planet in the right temperature band, but sitting in a star system with a tiny astrosphere, might face a much more aggressive radiation climate than Earth. And Voyager tells you what that means in actual flux numbers, not just guesses. Then you bring it back to engineering, because all of this becomes brutally practical if you ever want to send people, not just instruments, out where Voyager is. If Voyager shows that outside the heliosphere the galactic cosmic ray intensity at certain energies goes up by, say 50 to 100% compared to inside, then you can plug that directly into radiation transport codes and ask, how thick does my shielding need to be to keep crews within acceptable risk over a 20-year mission? The standard answer from decades of calculations is that you want the equivalent of tens of centimeters of water or similar hydrogen-rich material around crew habitats to knock down a lot of the dose from galactic cosmic rays. That might mean large water tanks doubling as walls, thick polyethylene, or more advanced layered materials. You might also consider active shielding using magnetic or electrostatic fields to deflect charged particles before they hit the hull, but that technology is still conceptual. Voyager doesn't design the shield for you, but it gives you the external numbers those designs must handle. the fluxes and energy spectra the system must survive for decades without failing. For electronics, the story is similar. Outside the heliosphere, more high-energy particles means more single-event upsets, more bit flips, more cumulative damage to detectors and solar cells. Engineers can look at Voyager's particle data, translate those fluxes into expected upset rates per chip, and design redundancy and error correction accordingly. You're no longer designing for an abstract deep space environment, you're designing for the actual interstellar environment just beyond the sun's bubble. So Voyager's radiation story boils down to this. Inside the heliosphere, you live under a combined shield of stellar wind, magnetic field, and planetary protection. Outside, you step into the galaxy's baseline storm. The difference is not infinite, but it is big enough that for biology and hardware it changes the rules. And that forces one more question. If the environment is that harsh, and the distance is that large, how do you keep a fragile, power-limited 1970s spacecraft alive and talking at 20+ billion kilometers, long enough to even measure any of this? How do you keep talking to a machine from the 1970s that's now around 24 to 25 billion kilometers away, and barely has enough power left to run a hairdryer? At that distance, about 15 to 16 billion miles, Voyager's main radio transmitter only pushes roughly 20 watts of power, less than a bright household light bulb. That tiny signal spreads out over a sphere with a radius of more than 160 astronomical units. By the time it washes past Earth, the power hitting our antennas is so small it's hard to compare to anything normal. It's far weaker than a whisper, more like trying to pick out a single grain of sand hitting a window somewhere on the other side of a continent. And yet, NASA's Deep Space Network, using giant radio dishes and extremely sensitive receivers, still locks onto that faint carrier and decodes a trickle of bits coming from the edge of interstellar space. That feat depends on the engineering decisions made before you were born. Voyager's high-gain antenna has to stay pointed at Earth within a tiny pointing error, or the signal drops below the noise. The radios use narrow-band, ultra-stable tones, so that the Deep Space Network can integrate the signal for long periods and pull it out of background noise. Engineers compress the data, lower the bit rate, and accept that sometimes they're going to be reading tens or hundreds of bits per second from a spacecraft older than most of the people managing it. Every frame that arrives is proof that the attitude control, the power system, the computers, and the antennas are still working together, across a distance where a command takes almost a full day for the round trip. Underneath that fragile link is an even more fragile power source. Voyager runs on 3 radioisotope thermoelectric generators, RTGs, which turn heat from the decay of plutonium-238 into electricity. Those RTGs lose about 4 watts of electrical power every year as the plutonium decays and the thermocouples age. At launch, the spacecraft had a few hundred watts to work with. Today, after almost 5 decades, the available power is under 250 watts and falling. That has forced NASA to shut down instrument after instrument, and even some heaters just to keep the core systems alive. In 2025, they even switched off Voyager 1's cosmic ray detector to free up a few more watts, a painful move given how important that instrument has been for all the heliosphere science you've just heard about. This is what a mission looks like when it's literally running on fumes. Engineers have to decide which instruments die first. They've already turned off cameras, spectrometers, and many planetary instruments that are no longer useful in interstellar space. They shuffle the remaining load, sometimes turning off heaters that keep hardware within its original temperature limits, and they monitor which components can tolerate the cold without failing. The current goal is simple: keep at least a few fields and particles instruments running into the 2030s, then accept that after that, there may only be enough power left to send basic engineering telemetry. On top of the power squeeze, there's the problem of staying pointed. Voyager carries small hydrazine thrusters to rotate the spacecraft and keep the antenna locked on Earth. Over decades, tiny bits of residue have built up inside the narrow fuel lines and valves. Some thrusters have clogged or become unreliable. That's where the recent 2025 thriller comes in. A set of roll control thrusters on Voyager 1 had been considered dead since 2004. Mission teams accepted the loss back then because the backup system still worked, and frankly, nobody was betting hard that the spacecraft would still be operating 20 years later. Fast forward to 2025. Voyager 1 is to about 24.9 billion kilometers from Earth, roughly 15.5 billion miles. The backup roll thrusters are aging and clogging too, and the only antenna on Earth that can send commands to Voyager, the big dish in Canberra, is about to go offline for months of upgrades. If the team doesn't fix the roll control before that downtime, they risk losing the ability to aim the antenna at Earth at all. So they go back to the dead primary roll thruster system, the one that hasn't worked since 2004, and ask a brutal question. Did we misdiagnose this 20 years ago, and is there anything left to try? The suspicion is that the problem might not be the thruster hardware itself, but a stuck state in the heater circuits that warm the thruster before firing. If they can flip that virtual switch back, the heaters might come on again, making it safe to use the thruster. The risk is high. Any mistake, and the spacecraft could misorient, fire thrusters in the wrong state, and damage plumbing that can never be repaired. They craft a careful sequence of commands, send it, then wait almost 23 hours for the signal to reach Voyager, and another 23 hours for the response to crawl back at light speed. When the data finally arrives, the heater temperature on the supposedly dead thruster has risen. The thruster is alive again after 21 years of inactivity. Newspapers and websites call it a miracle save, but from the inside it's the result of conservative design in the 1970s, obsessive fault analysis in the 2000s, and a careful gamble in 2025. A spacecraft older than almost everyone watching this video just had its attitude control partially resurrected by a software poke sent across 22 light hours from engineers who weren't even born when it launched. This isn't the first time Voyager's thrusters have been pushed beyond what anyone thought reasonable. In 2017, the team revived trajectory correction thrusters that hadn't fired since the early 1980s, using them to extend the life of the attitude control system. Since then, thruster swaps, heater shutdowns, and other tweaks have become routine survival tactics. Each change is followed by day-long waits to see if the spacecraft responded the way the ground simulations predicted. It's like doing surgery where every cut takes almost 2 days to confirm. So why does any of this matter for the future, beyond the emotional hit of old probes still alive? Because every one of these hacks is a real-world rehearsal for how to run interstellar missions when there is no quick fix, no on-site repair, and no high-power solar array to bail you out. Future interstellar probes will be more complex, but they will still have to deal with radioactive power sources that decline over time, thrusters that clog, valves that sickle and stick, computers that accumulate bit flips from cosmic rays, and antennas that must stay aligned across light-day distances. Think about how you'd design a new mission knowing what Voyager has revealed. You would plan for power decline from the start, maybe with modular instruments that can be shut down in stages, and a clear priority list on what science you want at 10 astronomical units, 100 astronomical units, and 1,000 astronomical units. You'd probably include multiple layers of redundancy and attitude control, maybe with electric propulsion or reaction wheels backed by thrusters, and you'd design plumbing that tolerates residue or self-cleanse better than Voyager's hardware ever could. You'd also design your communication system with the deep space network lessons in mind, possibly with higher frequency links, better error-correcting codees, and maybe relay probes parked farther out to reduce the single-hop distance. Voyager's bit rates tell you what's realistic when your transmitter is down to a few tens of watts, and your distance is measured in tens of billions of kilometers. That's not speculation, it's in the link budgets engineers are using right now. Every noise bump in Voyager's telemetry, every mysterious data glitch that gets debugged from billions of kilometers away, every instrument that gets powered off in just the right order to keep the mission going one more year, is practical training for the people who will one day fly something far more advanced halfway to the Oort cloud, or beyond. When those future probes are 50,000 astronomical units out, you won't be starting from zero. You'll be building on a playbook written now, by the teams keeping these two aging spacecraft alive on the very edge of what their original designers ever considered. But even with all of that ingenuity, power tricks, and long-distance repairs, Voyager is still on a one-way path. The RTGs will eventually fall below the level needed to power the transmitters, the instruments will fall jisto, and the spacecraft will keep gliding outward with no way to talk back. So the last big question becomes, what does that long, silent exit actually look like in terms of time and distance, as Voyager leaves the Heliosphere far behind and slowly drifts toward the Oort cloud and, eventually, the wider galaxy? Here's the part where your normal sense of distance and time just stops working. Voyager 1 is moving at about 17 kilometers per second, roughly 61,000 kilometers per hour, around 38,000 miles per hour, one of the fastest things humans have ever launched. At that speed, you cross continents in minutes. You cross the distance from Earth to the Moon in a few days. But on the scale of the solar system's outermost structures, that is still painfully slow. To reach just the inner edge of the Oort cloud, the spherical shell of comets that probably starts somewhere around 2,000 to 5,000 astronomical units from the Sun, Voyager 1 will need on the order of 20,000 years. To get all the way through that region and reach a distance of maybe 100,000 astronomical units where the Sun's gravitational grip on small icy bodies finally becomes comparable to the tug from other stars in the galaxy, you're talking about something like 100,000 years. That means everything Voyager is doing right now, all the data from the Heliosheath and the local interstellar medium is happening practically at the starting line of its long exit. The heliopause at approximately 120 astronomical units is just outside the track's first lap marker. Over tens of thousands of years, the spacecraft will keep gliding outward, its speed barely changing, while the Sun slowly shrinks to just another bright star behind it. On even longer timescales, Voyager 1 will do what every unbound object in the galaxy does. It will drift past other stars. Its trajectory, combined with the motion of nearby stars, means that in roughly 40,000 years it's expected to pass within a couple of light years of another star, often cited as Gliese 445 in the constellation Camelopardalis, at a distance of roughly 1.6 light-years or so. That's close in galactic terms, closer than Proxima Centauri is to us now, but still an enormous separation, trillions of kilometers, and it will take tens of thousands of years just to get that near. Chemical rockets, even with gravity assists, are incredibly slow compared to the size of the Milky Way. Voyager's entire journey so far, from 1977 to today, barely shifts its position on a map of the galaxy. Meanwhile, the clock on its power source is running down. The plutonium-238 in the RTGs decays at a fixed rate, and the electrical output has been dropping by a few watts every year. Engineers have already turned off many instruments and heaters, and sometime in the 2030s or 2040s the power will fall below what's needed to run the remaining science instruments and the radio together. At that point, the last bits of science data will be sent, the last engineering frames will trickle in, and then there will simply not be enough voltage left to keep the transmitters on. The spacecraft will still be out there, but for us, it will go dark. That data horizon is the real end of Voyager as an active mission, even though the hardware will keep flying. You can treat that moment as the end of Chapter 1 in interstellar exploration, the first time humanity has sent something across the heliopause, listened as it reported back on the galactic environment, and then had to let it go because physics and radioactive decay don't care about our curiosity. After that, Voyager 1 and Voyager 2 will just be inert objects on hyperbolic paths, drifting silently among the comet reservoirs and passing unnoticed through the thin gas of the local medium. There is one more piece that will keep riding along, even when the instruments are dead, the golden record. Each Voyager carries a copper phonograph record, gold-plated, with sounds and images from Earth and a diagram explaining how to decode them. It's often presented as a sentimental gesture, a message in a bottle to any hypothetical aliens that find it. But you can also see it as a scientific statement. Humanity didn't just send out a probe to measure particle counts and magnetic fields, it also attached a time capsule that says, "Here is who built this, and here is what our planet looked and sounded like," to the first spacecraft to actually measure the boundary between our star's bubble and the galaxy. Every detection Voyager makes now, every plot of plasma density or cosmic ray flux, is essentially the preface to that record. The spacecraft is not just leaving the solar system, it is characterizing the environment that the golden record is entering. If some distant civilization ever finds that disk, the space it's moving through will have been mapped, in basic physical terms, by the same mission that carried it there. So by the time Voyager is a silent chunk of metal drifting toward the Oort cloud, the measurements it sent back will already have changed how we draw the map of our own neighbourhood in the galaxy. And that sets up the final step in this story, pulling everything together. After all of this, what did Voyager actually teach us about where the solar system ends, what interstellar space is really like, and what it means for a technological species to step, for the first time outside its star's protective bubble? So after all of this, what did Voyager actually change in your picture of where the solar system ends, not as a slogan, but in hard numbers and clear boundaries? The first big answer is that the edge is not a clean line you can draw once and forget. Voyager showed you that the edge of the solar system is a moving, turbulent, asymmetric shield. It's a boundary defined by pressure balance between two plasmas, the solar wind blowing out and the interstellar medium pushing in, and it's warped by the local galactic magnetic field. Termination shock distances at about 83 to 94 astronomical units, different in different directions. A Heliosheath that swells and deflates with the 11-year solar cycle. A heliopause that sits around 120 astronomical units in two different hemispheres, but not at exactly the same distance. All of that tells you this is not a fixed shell, it's a breathing structure. When the sun's wind is stronger, the bubble expands a bit. When the external interstellar pressure dominates more, it squashes in. On top of that, you have wrinkles and dents set by the direction and strength of the interstellar magnetic field. So the edge of the solar system is really a dynamic, three-dimensional, asymmetric interface. Voyager didn't just cross a static border, it sailed through a boundary layer that moves by several astronomical units over decades and looks different in the north than in the south. That alone is a huge shift from the old picture of a perfect comet-like tail and a tidy line marking inside and outside. The second big answer is that interstellar space is not empty. Before Voyager, interstellar space sounded like an almost philosophical void. After Voyager, you can quote actual numbers. Plasma density outside the heliopause, about 0.08 electrons per cubic centimetre. Magnetic field strength around half a nanotesla. Temperatures in the surrounding plasma in the tens of thousands of Kelvin. Sound speeds in that gas in the tens of kilometers per second. Those numbers came from real instruments. Plasma wave tones that gave you density, magnetometers that gave you field strength and direction, cosmic ray detectors that tracked particle flux inside and outside the bubble. On scales of a few astronomical units, Voyager saw densities changes of tens of percent, magnetic field direction swings, and cosmic ray intensity variations. That is texture and weather in the galaxy at the scale of a single spacecraft. Space between the stars is thin, but it's not featureless. You can measure it, you can map it, and you can see that energy from distant supernovae and large-scale flows is still shaping it right where the heliosphere pushes in. The third piece is about what the heliosphere itself really means for life and for future travel. Voyager's particle data make it clear that the heliosphere acts like both a cradle and a gate. As a cradle, it has helped make Earth a relatively gentle radiation environment. By modulating galactic cosmic rays, especially in certain energy bands, the heliosphere cuts down the flux that reaches Earth's orbit. On top of that, Earth's magnetic field and atmosphere add more protection, but the heliosphere is the outermost layer of that shield. Voyager's measurements of galactic cosmic ray levels inside versus just outside turn that from a guess into a quantified effect. As a gate, the heliosphere is the boundary any future interstellar mission has to cross. Inside, you are in solar space, dealing with solar storms, solar energetic particles, and a certain level of galactic background filtered by the sun's wind. Outside, you are in galactic space, dealing with the raw, interstellar spectrum. Voyager showed you what that step looks like in real data. particle intensities shift, plasma densities jump, magnetic behavior changes character. That means mission planners don't have to imagine the crossing, they can design for it. Radiation shielding, communications, navigation, everything can be tuned using real measurements from the actual edge. You can also extend that logic to exoplanets. Every star that blows a wind carves out an astrosphere. If the wind is weak, or the external medium is dense and strongly magnetized, the astrosphere shrinks. Planets that might otherwise sit in a nice temperature range could be exposed to much higher background cosmic ray fluxes than Earth, simply because their star's bubble is smaller or more compressed. Voyager's numbers give you a baseline for what outside the bubble looks like, so when you model other systems, you're not guessing blindly about how their radiation environment might compare to ours. The last piece is the psychological shift. Before Voyager, you could say, we live in the solar system and the Milky Way is outside. But that boundary was abstract. It was a line in diagrams, a concept in textbooks. Now you know where the sun's plasma stops and the galaxy's plasma begins, along at least two directions in space with error bars and units attached. The line between our system and the galaxy is no longer just words. It's a real force that has been crossed by human hardware moving at about 17 kilometers per second. Voyager drew that line using particle counts, plasma densities, and magnetic field angles. It showed you that the solar system is not just a stack of orbits around a star. It's a bubble of hot, magnetized plasma ploughing through a larger, colder magnetized medium. From the inside, under a thick atmosphere that's invisible. From Voyager's vantage point, it's the main feature of our local space environment. So when you say we're in the solar system now, you're really saying we're inside a star's protective bubble, inside a galaxy that is full of structure and radiation. And because two aging probes from the 1970s kept flying, kept counting particles, and kept sending back data from more than 20 billion kilometers away, you don't just believe that on theory, you have direct measurements of what it feels like at the edge of that bubble. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.